All right. Sorry, everybody. I goofed. I started myself over here, and I forgot to go live. So back it up again. Welcome back to CS 125. I'm excited to have you guys today. So I'm going to start to put up some musical selections on the cover slide. We're a little bit behind today. I apologize for that. So I'm just going to kind of race through this. Today we're going to talk about lists. We're going to use lists. So you guys have just completed yesterday the implementation of the simple ArrayList class, right? That's a class that implements the list interface, and it does so using an array internally. Starting today, you're going to implement a different type of list. This is a list that implements the same interface. So from the perspective of the user of the list, it behaves identically, but it implements that list using links instead of an array, right? And this is going to be a huge amount of fun, I hope, because not only is this a fun piece of code to write and a fun, simple data structure to implement, right? So now, in the future, when you use a list in Python or you use a list in Java, you'll have some sense of what's actually going on inside that list, right? Because you've built it, right? You could actually use your ArrayList. It's not quite as sophisticated as the actual ArrayList class that Java provides built in for you, but you could use your ArrayList in place of Java's ArrayList, and it would work fine. But the real reason we're doing this is not only to give you practice with imperative programming, which we haven't really done much of for a little while, and it's not only to give you practice with object references, which we introduced you to before break and are going to play a big role in how we implement lists using linkage, which we're going to talk about today, but the real reason we're doing this is to get some practice analyzing algorithms. Because it turns out that despite the fact that the ArrayList and the linked list behave identically, so from the perspective of the user of the interface, those two implementations behave the same. But internally, they're implemented very differently. And it turns out that those two different implementations produce different performance trade-offs. There are certain operations on an ArrayList that are quite fast that on a linked list are slow, and vice versa. There are trade-offs here. So this is one of, this brings together lots of the fun stuff that we get to do throughout the rest of the semester together. We get to build data structures, which is fun, gives us a chance to do some neat programming. We get to analyze their performance, which starts to build up our intuition about how algorithms behave. And then we also get to talk about the trade-offs here, right? Because whenever we talk about the two different algorithms for solving the same problem, the only reason we typically do that is because they're good for different things. One of them performs well under certain conditions, the other one performs better under other conditions. And so one of the parts of being a computer scientist is being sophisticated enough to choose the right algorithm to solve a problem. This is sort of like if you are, a carpenter choosing the right tool for a particular problem, right? And this is something that you will take a lot of time and practice to get used to, but you will get good at. So as a reminder, in CS 125, when we analyze algorithms, our main goal is to be able to build intuition. We want you to leave this class with an intuitive sense of the performance differences between different ways of doing things. Once you get on to 173 and 225 and 374 and other classes later, those classes will introduce you to algorithm analysis in a much more mathematical sense. Because once we've written down exactly how to solve a problem in a way that's so specific that a computer can actually do it, we actually have a great starting point for analyzing that algorithm in a particularly rigorous way. When you get to 173 and 225 and 374, you'll actually prove things about how long an algorithm takes to run, which is incredibly cool. We're not going to do that in 125. That is beyond the mathematical maturity that we expect of you in this class. But I do want you to leave with this intuition, right? With a feeling, kind of a gut feeling that you can look at a particular algorithm and say things, particularly by looking at the implementation, which is something that we'll do today, about how long it's going to take, right? So as a review from last time, algorithm analysis is this process of taking an algorithm and being able to make statements about how many resources that algorithm is going to take to solve a particular instance of a problem, right? And those resources might be time, might be the amount of computational resources, it might be memory, how much memory on your computer does the algorithm take as it runs. In other cases, we won't talk about them in this class, but it might be things like how much network bandwidth does it require. There's a lot of different resources that we can potentially think about, right? We'll typically think about memory and CPU as the primary things that we analyze, and particularly CPU or runtime. time. How long does it take, right? So when we analyze algorithms, we're typically interested in how well they perform in the general case. We don't usually care about how long it's going to take an algorithm to solve a specific problem. Instead, because typically we're talking about code that's going to get used to solve lots of different types of the same type of problem. And so we want to be able to say, in the general case, how long does it take, right? And particularly as the problem gets really big, how long does it take? One of the reasons we typically talk about limiting performance for algorithms, which means how long does it take on an arbitrarily large list or arbitrarily large number or whatever, a particularly large instance of the problem, is that there are certain parts of the algorithm that don't scale with the size of the problem. So if you remember back to last time, we practiced our algorithm analysis skills on the GCD algorithm. And our simple brute force GCD algorithm had a first part where it found the minimum of the two numbers. That always takes the same amount of time no matter how large those numbers are. Then we get into a loop, and that loop takes a different amount of time depending on how large the two numbers are. That loop runs longer and longer and longer the bigger the numbers get. That part at the top where we computed the minimum, that always takes the same amount of time. So when we talk about how long it takes to solve an arbitrarily large problem, we get to ignore these parts of the solution that don't scale with the size of the problem, right? And so that allows us to do is zero in on the parts of our algorithm or the parts of the code that are actually going to take longer and longer and whose runtime is related to the size of the problem. Now, when we talk about algorithm performance, like I said, we don't want to talk about specific inputs, but frequently we need to divide our inputs into different categories because different algorithms perform differently depending on features of their inputs, right? So sometimes there's a particular input for an algorithm on which it performs extremely well, and there's another input for that same algorithm on which it performs extremely poorly. So when we talk about performance, frequently we'll distinguish best case, worst case. We want to know, in the worst possible case, how long will the algorithm take? And then it's also helpful to know, hey, the algorithm might finish really quickly, and here's why. And then sometimes we'll try to think about this average case runtime, right? An average case runtime turns out to be much more complicated to consider because the average case runtime ends up depending on the inputs that we feed the algorithm. If we always feed the algorithm inputs on which it performs really poorly, then our average case runtime is very close to the worst case runtime. If we always feed inputs to the algorithm which it performs extremely well, then our average case runtime might be very close to the best case runtime of the algorithm. And this is something that people think about when they choose algorithms for a particular problem. So the other thing that we're going to be talking about, and this is going to again come back to our list conversation, is, and I apologize if I just said this before, I started this lecture and then I forgot that I wasn't streaming, and so I restarted it, and so I can't decide if I've said this, but I feel like I should say it again because it's kind of important. So here goes. When we analyze algorithms, we compare two algorithms for solving the same problem. Usually what we're doing is we're actually thinking about trade-offs. One algorithm is good at one thing, another algorithm is good at another thing. When we talk about lists, we're going to see that the type of list that you just finished building on yesterday's homework is good at certain types of operations, whereas the type of list that you'll start building on today's homework, despite the fact that it behaves identically from the perspective of a user of the list, has very, very different performance. Okay. And last time we also introduced this idea of big O notation, right? Big O notation is mathematical notation that describes the limiting behavior of a function, right? When the arguments get really big, right? So how does the performance or the runtime or the resource usage of that algorithm change as we make the inputs very large, right? We saw that some algorithms grow, the runtime or the resource usage grows linearly. Some algorithms, it grows exponentially, like n squared, right? There are other algorithms where it grows logarithmically, like the logarithm of a number, right? Which grows much more slowly than that number, right? So essentially, we want to estimate what happens as the problem gets very hard, right? And for the purposes of 125, again, what we're focused on here is building intuition about algorithm runtime. And so we're really going to focus on these complexity classes. So we're going to look at things like, what's the difference between an algorithm that takes O(n) squared and an algorithm that takes O(n). And you can see that that difference can be pretty dramatic. So the O(n) algorithm or the linear algorithm is down here in the green. The n squared algorithm is in this sort of tealish color. And you can see even after the problem only starts to get kind of medium size, there's a huge performance difference between these. And so if you can find an algorithm, if you have an algorithm that's currently solving a problem that's running in ON squared, and you can find an ON algorithm for that problem, you can increase the performance dramatically. And that's pretty cool. All right, so now let's talk about lists, right? So the algorithm, the data structure you guys have been building on the last couple homework problems, which have kind of served as a nice review of some of our object-oriented principles, also our imperative programming background that we talked about for the first half of the class. What you guys have built, finishing yesterday, is this general purpose data structure that's called a list. You can think of a list as a generalization of an array. Like an array, it puts items in order. It brings order to a set of data values. And in doing so, that's the structure that the list data structure brings to the underlying data, right? I take a bunch of, sort of ordered data values, and I put them in a particular order, and that order is very significant, right? That order is the difference between something sounding like beautiful music, a series of measurements of air pressure over time, ordered properly, and something sounding like static, if I take those same measurements and just jumble them up and disorder them, right? Lists are a generalization of arrays in the sense that, like an array, I can get and set values at any index. But unlike an array, I can also perform operations that add or remove data from the list. So with Java arrays, you remember, once I create an array of size 8, it's always going to have size 8. There's no operation I can do on that array that causes it to have size 9 or size 7, right? If you've worked in Python, you work with lists. If you've worked in many other programming languages that have a list, JavaScript, Python, the list is long of languages that have some idea of a list, this might have seemed weird to you, right? In Java, if I have an array of 8 items and I want to, create an array of 9 items, if I want to add something to it, I have to create a new array with 9 items and copy everything over. You guys have seen how that works with your lists, right? Lists are a tremendously powerful data structure. They get used all over the place for solving real-world problems, right? I think between lists and another data structure that we'll talk about in a few weeks called map, these are what I refer to as the 2 data structures that you meet in heaven, right? Together, you can use them to solve lots and lots and lots of problems, right? You will go on, you will learn about much more sophisticated data structures. We'll talk about some in this class, trees, graphs, all sorts of cool stuff. And those are tremendously interesting and important for solving certain types of problems. But for 80, 90% of the software that you might want to write to change the world, you can get away with using just a combination of lists and maps. So, and one of the things that makes lists so fascinating and makes this whole subject that we've entered into in this part of the class so fascinating is this idea that where there are these trade-offs, right? So depending on how we structure our list internally, 2 things that conform to the same interface may perform differently. This is also a great place to remind you guys about what an interface is, right? So your list is a provider of the simple list interface. You have now produced one implementation of something that provides the simple list interface. Starting today, you'll produce another implementation. Those 2 implementations work incredibly differently, but from the perspective of somebody using your list, they work identically, okay? Except for the fact that they have different performance trade-offs that we're about to get into, right? So we're going to look at this with lists, but we'll come back and we'll talk about this when we get to sorting, and we'll talk about this when we get to trees. The data structures that you guys start to create, whether or not it's in this class or downstream in 225, they exist to enable algorithms. Remember? So there's this really beautiful relationship between these 2 topics. Data structures exist to enable algorithms. We create a data structure because it means that a particular algorithm now runs much more efficiently on top of that data structure, okay? So what we've done so far is we've built a data structure, a list data structure using an array. And those arrays, that array-backed list, has this property that lookups are fast. So get and set is quick. But modifications to the array, things that change the size of the array, whether I'm removing elements or adding elements, are slow, okay? Now, the data structure we're going to look at today which is a different implementation of a list that's called a linked list, these have different performance trade-offs. So in contrast, a linked list, to look up get or set on a linked list is actually O(n). However, some insertions into that linked list are fast. Some of them can be as fast as constant time. Now it depends on where you're putting things into the list, and again, we're going to get into this and look at it together. But just keep in mind that there are certain types of operations on linked lists that can be very fast, right? So again, great trade-off here, right? List backed with an array, fast lookups, slow modifications. List backed with a linked list, slow lookups, some modifications are fast, right? And it turns out that the places where I can quickly modify a linked list, those locations that are fast turn out to be very useful because they're common places where algorithms add or remove data from a list. And both of these also present different memory usage trade-offs that we'll discuss along the way. Okay, and this is, the Java, just as a review, this is the Java list interface. Both of the lists that you guys are implementing actually exist in Java, right? So if you look down here, you can see that so this is the list interface. For now, please ignore these brackets. This is something that we will talk about in the future. This is something known as generics. We'll get there a couple weeks. We'll talk about generics in class. But for now, what you can see is that, if I look here in the Java documentation, this says these are classes that implement this interface, right? One of them is an array list. And this is one of the more common lists that you use when you write Java programs. You guys are using this on MP3 right now. The other one, but down here, here's a linked list, right? So both of these two list implementations are legit, right? Like Java actually has them, has official implementations of them. And so, these are not strange things. These actually get used by real programs. And let's see here. All right, so in contrast, here's our list interface. The official Java list interface is pretty gnarly. It's got lots and lots of methods and stuff like that. So if you look, it has all of these, and some of these are things that we don't want you to have to implement, right? And so what we did is we created a simple version of the Java list interface for you to work with. And this is what you've been working with for the past couple of homework problems. Our lists have a get and a set. The get returns an object reference for the particular index, and I think it's supposed to return null if that index is invalid. Set sets the index at a particular point in the list to the past object reference. Add and remove modify the length of the list. So add inserts. In some lists, this is called insert, right? It inserts the object at that point in the list, right? So after add completes, the object that is passed is at index in the list, and anything that was in the list after that point has been shifted over, right? So if I insert something at the beginning, if a list had 4 elements, I add something to index 0, that object is now in index 0 on the list, and everything else has been shifted over by 1. So the thing that was at index 0 is now at index 1, the thing that was at index 1 is now at index 2, etc. Remove works the other way. So remove takes an item out of the list and returns it to the column. So after I run add, my list that had n elements now has n plus 1 elements. After I run remove, my list that had n elements now has n minus 1 elements. And finally, to make it easier to program with our list, we added a size method. Okay, and so here is, I think, an actual, is this complete? Yeah, I think it is. Oh, maybe this one only has remove. Yeah, so this is an implementation of an array list. I think at this point you guys have done pretty much all of the different components of this on the homework problems. But we can sort of go over this a little bit. And one of the reasons for doing this is to actually be able to see together how long some of these operations take, right? So let's run this code and make sure it works, right? I created a list initially with, I can put some extra elements in here. And now what I'm doing, so I create a list, my constructor up here takes an array of objects, and what it does, it initializes the list to have the same references that are in this passed array in the same order. And this works by actually modifying the private array of objects that the list maintains internally. Okay, so let's actually kind of walk through this implementation, right? So this is an array list. Internally, it has a private array of object references. This is where the things that are stored in the list actually get put by the array list implementation. Okay, my constructor goes through the passed array and essentially copies the object references. I'm not copying the objects, remember. I'm just copying the object references into my array if I pass a non-null array. So essentially it initializes my array to be the same size as the passed array, original array.length. And then I write a loop where I go through my original array and I copy each reference into the corresponding spot in my private array. So now let's look at get and set. Right? Get takes an index, and that's the index of the element to return. The first thing I need to do in get is I need to check to make sure my index is sane. And there's two ways in which the index could be bogus. One is if you pass me a negative index, and the second one is if you pass me an index that's greater than or equal to the length of my internal array. So if my list has 4 elements, valid indices are 0, 1, 2, and 3. This is just like an array. So if you pass me an index 4, that's an invalid index. And so I check for invalid indices and I return null if you give me a bad index. We will, when we talk about exceptions in a couple of weeks, talk about a better way to handle cases like this. But for now, what we've asked you to do is if we pass an invalid index to get, it should return null. Otherwise, I just look up the object in my array. And remember when we talked about the different complexity classes, we pointed out that typically looking up a value in an array is constant time. Okay, so let's think about what the runtime is of our get method. Okay, I've got, and you know, whenever we do runtime, we always look for things like loops, conditional expressions, whatever, right? So, you know, all I see in my get method, there's a simple conditional expression here that's checking the index, and then I look it up in my array. So this is a constant time operation. Okay, set works almost identically, right? Set has the same check for the index that get has, and then instead of returning the value of that index, it actually modifies the value of that index. So it takes the index, now I know the index is okay, and I just set it equal to refer to the object that was passed, right? So these two operations on an array list are constant time. They're both constant time. You can see no loops, you know, these are like 3 or 4 lines of code. These are really simple, you know, and that's actually one of the great things about array lists, right? Get and set are easy, okay? When we get to linked lists, we're gonna see that it's the opposite. All the complexity in a linked list, or some of the complexity, is in get and set. All right, size is also extremely simple. All I do is return the length of my internal array. Okay, but now let's look at remove. And add is very similar. I'm not going to implement add because I think you guys have already done that. But here's remove. Okay, and remove is much, much more complicated than get and set. Okay, first thing I do is an index check. That's what's happening here, lines 35 through 37. Then once I know that the index is valid, the first thing I do is I grab a copy of the object that's currently in the array at that position. This is the object that I'm going to return. So you can see when I return a reference to this object. And this is the only place this variable gets used in the code. It doesn't get used in here at all, right? So, and the reason I'm doing this is because I'm about to overwrite the array. And so I'm about to lose a reference to this object. If I didn't grab it now, when I got to the bottom, it wouldn't be there anymore. Or there would be a different object located in the same place, right? So at this point, I haven't modified the array at all yet. So I grab a copy of the reference at that position. And then the work of this function really happens here. And what I'm doing here is I build a, first of all, I create a new array. That array is 1 unit smaller than my current array. Remember, remove, if my array has size n, when remove finishes, my array is now going to have size n minus 1. Then what I do is that this code goes through the new array, and what it does is it maintains 2 indexes. One index is maintained by the loop, and the other index is maintained here outside of the loop. So really what I have here is I have a loop with two indices, okay? One index is indexing my original array, and one index is indexing the new array. And the trick is, normally they move forward together, but there's one place where the index that's indexing my my original array, the longer array, needs to jump forward one. And that's what happens right here. So you'll see normally inside my loop, every time I go through, I'm incrementing new index in the loop body, in the loop statement, and I'm incrementing original index in the loop body. But there's one place when new index is equal to remove index that original index jumps forward an extra spot. And that's how I skip the element that I'm removing. Then all I do is I'm copying references from my current array to this new array that I created right here that's a little bit smaller. When I'm done, I modify the reference that the class is holding internally to the array to point to this new array that I just created that's 1 unit smaller. So essentially what this is doing is it creates a new array that's 1 unit smaller, and then it copies everything from the original array into that new array except for the object located at the index that I'm removing. That's why this if statement is here. Okay, so now that we have some understanding of how this works, and again, you guys have, I think, implemented add already, what's the runtime? So let's look at this, okay? And you know, this is a lot more code to look at than we've had to look at for get and set. But the trick is whenever you're doing algorithm analysis, you know, look for things that might take longer and longer, right? Or things that might take a variable amount of time depending on what the inputs are, okay? So here, you know, this type of stuff, this is going to take the same amount of time. This is going to take, you know, the same amount of time. This is just looking up an object in an array. But this loop, right? This for loop, the longer new array is, okay? So new array, the size of new array is essentially almost the same, particularly if my object array gets really big, the size of my new array is almost the same, right? If my original array had 10 billion elements in it, then my new array has 10 billion minus 1. Those are almost the same length. My for loop has to go through every single element in that array and copy over these references one at a time. It's essentially filling that new array with a copy of references from the old array, but in order to do that, it has to walk through the old array one index at a time. And so as my array gets bigger and bigger and bigger and bigger, this loop is going to take longer and longer and longer, and it's going to take longer proportional to the size of the array. And so for an array list, removing an element is O(n), where n is the size of the list. So when I have a small list, removing the element will only take a few steps. If the list gets bigger, it's going to take longer. If it gets bigger and bigger and bigger, it's going to take longer, and it's growing linearly. So it's growing at the same rate as the size of the list. So this is an O(n) operation. The add implementation you guys have done probably looked very similar to remove. It's also O(n), because it's going to do the same thing. It's going to create a new array that's a little bit bigger, and then it's going to copy all the data from the original array into that array, and it's going to add that element that gets passed. Okay, so again, these two functions look very, very similar to each other. And add is also going to be O(n). So this is just sort of an example of the kind of analysis that you do when you're trying to get an intuitive sense of what the runtime is for a particular algorithm, right? I go through the algorithm, I look for loops, I look for, you know, conditional expressions that might break out of the loop. The other thing you'll notice here is that there are no break statements or return statements inside my loop. No matter what the data is like inside the loop, I always go through the entire thing, right? I always have to copy everything in there, right? Some of the algorithms you look at won't have that behavior, but this one does, right? It does not exit the loop early, ever. So this is what we do, you know, to analyze this algorithm, right? So, you know, this gives you a sense, you know, now you've been warmed up, you're back to imperative programming, working a little bit with ArrayList, which is awesome. This gives you a sense of exactly what the runtime is of this particular set of operations on this type of data structure, right? So again, now we can start filling in this table that in a couple of classes, I think actually as early as Monday, we're going to fully flesh out with both ArrayList and linked lists so that we can see the trade-offs side by side. For an ArrayList, the get and set are fast. They end up just being an array lookup. Add and remove are slow, right? They grow slower and slower and slower as the list gets bigger and bigger and bigger, and they grow slower at the same rate, linearly. Okay. So I'm going to go check see if there's any questions. It doesn't look like there are yet. Okay, great. If you have questions, go jump on the question thread that's on the forum. All right. So just as an aside, I'm not going to spend too much time here. You might be thinking, are there ways to optimize the performance of this so that we can make this a little faster, right? And the answer is yes. And actually, real implementations of array lists don't change the size of the array every time, because that requires copying all of those values, right? Instead, what they do is they maintain internally an array that's bigger than you need, right? So if your array contains 3 items, the ArrayList implementation that you use in Java might already have allocated an array of size 64 or something like that, right? And so the idea is when you add the 4th element, the 5th element, the 6th element, it doesn't have to reallocate a new array. Instead, it just copies things around in the array that it already has, right? And so this can cause things to speed up a little bit, because it turns out that in Java, when I have to go and ask Java for more memory, that also takes time, right? So this line right here also slows my program down, because now I'm basically telling Java, hey, I need you to create a new array for me. That takes time. So if I can avoid doing that every time I create the array, that's a win, right? Now, what happens when that array is eventually out of space? Well, then the implementation will go and get a lot more, right? So you might start with an array that internally is size 16. Once your list gets to 6 to 17 elements, it says, okay, well, obviously you're serious about this whole list business, and you're gonna put a lot of stuff in here. I'll go out and I'll create an array of size 64. And then when you get to 64 elements, the implementation may be like, oh, wow, okay, this list is really gonna be big. I'll go out and get something that's size 256. You hit that, then it goes and gets 1024. You get that, maybe it gets 16K. Basically it's sort of trying to determine how long, how much space you're going to use, and every time you run out, it will get even more, right? Because it's trying to find a point where it doesn't have to ask Java for memory again. And so, the add and removes at this point are still going to be ON, but not having to allocate memory every time is still going to help, right? So this is a trick that real ArrayList implementations use to improve their performance a little bit, right? Now, again, there's always trade-offs here, right? So what's the trade-off here? The trade-off is that there's wasted space. I'm wasting memory. When you have a list that has 4 elements, but internally that array list has an array of size 64, there are 60 slots in that array that are empty. They're just sitting around unused. And so that's the trade-off, right? Now, on today's systems, your computers have just a ginormous amount of memory. I mean, it's like astonishing. I just got a new laptop and it has like 16 gigabytes of memory. I mean, that's just a shocking number. I mean, when I was a kid, back in the day, I think when I was in college, I had a computer that had like, I don't know, it was like a desktop computer. It might have had like a gigabyte of memory, and that was like a lot. Maybe it was only 512 megabytes, and that was a lot. I mean, things have come a long way. So this is one of the things that's fun about computer science as a field, is also that the parameters keep changing, right? If you had told people back then, like someday you're going to have a laptop that's going to have 16 gigabytes of memory, and I have a desktop under my desk at work that has 64 gigabytes of memory, they would have been like, oh my gosh. I mean, my hard drive when I was in college, I think was 16 gigabytes, right? Now I have that much memory on my machine. So things have changed. And so now, if you think about, is it worth wasting some memory in order to make something a little faster? The answer is normally yes, because you've got memory to waste, right? Your phone has more memory than my desktop did 20 years ago. All right, so the Q&A doesn't work quite as well here. I'll certainly invite questions about ArrayLists if you have them in the chat, but I'm going to move on. We're a little bit behind schedule today because I got off to a late start. So let's talk about this other option that you guys are going to start implementing today, and that's something called a linked list. the name says something about what we're about to do here, okay? So rather than using an array, what we're going to do is we're going to store the structure of the list by linking items together. So each item in the list is not going to know what index it is, but it's going to know the next item in the list, okay? And so if I start from the beginning of the list, I can count until I get to the right place in the list, right? So a way of imagining this is sort of like what we did when we talked about references. Imagine that, for all the students in the class, I gave you a piece of paper with the name of another student. Now what I've done is I've created a list, okay? Let's say I have the name of a student. So that student's the first student in the list, okay? So now I go to them and I say, okay, well, who's next? Who's after you? And they say, okay, here's who's on my piece of paper. And then I go to the next student, right? They're the second student in the list, right? I can ask them, who's the next student? They give me to the third student. So nobody in the list knows how long the list is. Nobody knows what index they're at. All they know is the next person in the list. But if I know who the first person in the list is, I can count all the way until I get to the nth person. So if I'm looking at person 72, I start with person 1, I use them to get to person 2, I use them to get to person 3, I use them to get to person 4, and I keep repeating that process all the way until I get to person 72, right? Now you might be thinking, hey, that's interesting because when we looked up items in our array list, it was O1, it was an array lookup. But now it sounds like there's this process you have to repeat to get to the 72nd person in the list, and you're exactly right? And that's one of the trade-offs here. But let's look at some of the data structures we're going to need to solve this problem, okay? So what we're going to do in our linked list is that rather than storing object references in an array, we're going to wrap each object reference that we store in our list in this item class, okay? So here's the class over here on the left. Each item has a reference to an object called value. That's the thing that we're actually storing in the list. But it also contains a reference to the next item in the list called next. Now, if this is null, it means that there's no more items in the list. So at some point, in my list of students, I would have to get to a student and I would say, who's the next student in the list? And I would say, I don't know, there's nobody after me, right? So there's always an end, okay? But if you're not the end, then what this reference holds is a reference to the next item in the list. And here's my simple constructor. Okay? So now let's look a little bit at how we could actually use this to create a list. Okay? So what I have on the left is a reference items that I'm using to refer to my list. And at first, I initialize it to refer to a single item. I stick an integer into my list. I'm using this, this boxing class that we talked about last time to convert an integer, an int literal, into a capital I integer so that I can use it as an object, right? Now, the list is empty before this, and so there's no next element here, okay? So here's what things look like in my world right now. I have a reference called items, and it refers to a single item. And that item contains the value 0. Now let's look at how I would add something to it. Okay? So now I'm modifying my items reference to refer to a new item that has value 8, and I'm setting its next reference to refer to the start of the list. So remember, right to left, this is the place where we have to review our right to left assignment. So I create a new item. The next reference in that item is whatever the start of the list was before. The start of the list when I started executing this was the item with value 0. Okay? So the next reference here on item 8 gets set to the item with value 0. Then I change my items reference to refer to the item that's returned. And so now look what I have. I have something that's starting to look a lot like a list. I have this items thing that's the front of the list, and then I have 2 items that are following. Okay, and so that looks pretty good. Okay, and now I can add other items to the list. So now I'm adding a third item. Okay, you'll see that that item is at the front. Now, so far, the only thing I can do is actually add things to the front of the list. But what I've done is I've built a list, and I know that some of you guys are going to have to come back and review this. This is tricky, right? And we'll go over this again on Monday. But what I'm doing is I'm building a list. I'm building it this kind of unusual way where I'm putting things in backwards. The items that I add end up at the front of the list, and the items I added previously are now being pushed to the end. And that's okay. We'll figure out how to deal with that later. You guys will write a version of insert for linked list that can put an item anywhere. Okay, but this is how things go. Now again, let's look at this list. So what does item 5 know about the world? All it knows is I'm not the last item because I have a next reference, and here's the next item in the list. What does item 8 know about the world? All it knows is I have a next reference to an item with this item here that has value 0. What does the item with value 0 know about the world? Its next reference is null, and so it must be the end of the list. So let's say I wanted to find the second, the value with index 1, the second item in my list. I start at the beginning. I used items to get to the first item in the list, which is the item with value 5. I use its next reference to get to the next item in the list, which is the item with value 8, and then I'm done. So essentially I have this iterative process that by starting at the front of the list, I can use to reach any item in the list. So here's the class that you guys are going to be working with for the next few homework problems. One of the things about this class, and I'm not sure if we talked about this a lot last time, is that it utilizes this idea of an inner class. So my outer class is called simple linked list. It's going to implement the simple list interface, and you guys are going to get a chance to finish up most of the same methods that you implemented for an array list, but the implementation for a linked list is going to be quite different. The item class here is actually an inner class. So this is a type of object that's only used internally within my simple linked list implementation. The only thing, this is kind of cool actually, it's kind of a neat thing about linked lists. The only thing the list needs to know is where the start of the list is. So it maintains one private field, private variable. The type of that is item, and I'm going to call it start. That is a reference to the start of the list. If I know where the start of the list is, I can find any other item in the list by what we call walking the list. I start at the beginning. I use the start reference to get to the first item. I use its next reference to get to the next item, and I continue this process until I get wherever I want to go. So again, this is an example of a Java inner class. This is known as a nested inner class. Inner classes can be private, and inner class methods have access to variables in the enclosing class, even if they are marked private, right? So if I implement a method inside my inner class, it can access private methods and variables of the simple linked list class. Okay, and here, why are we doing this from a design perspective? We're doing this because nobody outside the list, my simple linked list class, should know anything about the item class. So the users of the simple linked list class are going to use the interface simple list. So if I look at simple list interface, there's no item in here at all. It works with objects and indices, right? Get and set based on an index and an object reference, add and remove based on indices and object references. There's no list item there at all. So again, this is a good chance for us to review this separation between the user and the provider of an interface. Here, the provider of the interface is simple linked list, right? It's going to provide the methods that are required to implement simple list. How it does that is not your problem, right? The simple linked list is like, look, leave me alone. I know I'm a little different than an array list. I'm going to do things my own way. I have this idea about how I'm going to implement a list. I'm going to do everything that you say I have to do to be a simple list. I'm cool with that. I can do get, I can do set, I can do add, I can do remove. I'm going to do it my way. I'm not using an array. Don't like arrays. I'm going to use linkage instead. Leave me alone. Let me go about my business. Right? Okay. So this is this is our starting point for the next couple of homework problems. Let's talk about a specific thing that we can do in our one building block for simple linked list. The way that we approach them is going to be a little different than how we approach lists, our array lists. So here's an add to front method, and this actually works, right? how does this work? So it says it sets the start reference to be a new item. So basically this will put a new value at the front of the list. How do I do that? I create a new item over here. That item contains a reference to the value that's passed. That's what I'm storing in my list. And as the next reference, it refers to whatever the current start of the list is. So this is a way to put an item in the front of the list. Then I change my start reference to refer to this new item. This new item is now the first item in the list. Okay? This is essentially what we did back here, right? This is a version of this where I'm adding things to the front. I've wrapped this inside a method now, but it's the same code, okay? And so, just to give you a little bit of a hint of where we're going with this, when we look at this particular function, right, what is, like, if I'm talking about algorithm analysis, how long does this take to execute, right? So here, normally when we talk about ArrayList, the feature that drives performance, or N, is the length of the list. But what's the runtime of add to front? Add to front actually executes in constant time. There is no loop here. It's a single line of code. There's no loop. There's no conditional statements. It's just done, right? We're just finished. And so I promise that the linked list had this cool feature where certain insertions were fast, right? Depending on where they are in the list. So inserting things into the front of the list is quite quick. Okay, so I'm going to leave. You guys have some work to do on today's homework problem. In terms of getting started with linked lists, I'll be available, as will the CAs, to help with that. What I might do is actually extend that homework problem over the weekend so you have a little bit more time to work on it. I'll take questions on the forum. A couple of announcements. So, obviously we're still in this brave new world together of figuring out how to do this virtually. I'm definitely very interested in hearing feedback from anybody on the forum about how things are going. The quiz looked like it went off pretty well. We will do the same thing for the midterm next week. So if you think that there's a big problem with how we approach this, please let us know so that we can make some adjustments. We're starting to drive people to our new help system. I had some good interactions with people on that system yesterday. There's some bugs that I worked out overnight that I think will help today, but we're going to keep trying it. And check in with us too, right? I mean, look, we care about you guys. We miss you. We really want to support you through the rest of the semester. I want you to learn this material. I want you to succeed in the future. I think more than ever now, we need people with some of the skills that you guys are acquiring in this class. And there's going to be a huge opportunity for people that can build things, that can think about problems to help sort of deal with whatever the fallout is from the situation that we're in right now, right? So please stick with this, but check in with us, right? Write on the forum just to say hi. Send me email. I actually do answer email from time to time. Be happy to hear from you just how things are going. I know that you guys don't get a chance to come in, be part of a community, whether it's in class, whether it's in office hours or labs, and those experiences are important, right? So please join us on some of the video chats we've been doing. Say hi on the forum, reach out to people on the course staff or to me or whatever if you just want to talk or just want someone to know that you're there. Other than that, have a great weekend. I will see you guys again virtually on Monday.